this semester off with 100% on the test. Yeah. Logan would, but he doesn't think he will. Is that what you said? Yeah. All right. So I'm not going to write all these out, but effective nuclear charge is essentially the attractive force of the nucleus on its outermost electron. Well, that's how you calculate nuclear charge, but that's not how I would explain it. Sure. It's essentially the attractive force between the nucleus, or the protons in the nucleus, and the outermost electrons in an atom. All right? Now, Brandon is not wrong. He showed me the math. But we're in science, so we like word answers more than number answers sometimes. All right. Then we ready for these? So which one of these two is bigger and why? So who thinks that they know the answer to this? All right. Thank you, Mr. Jex. Why?
Because there's less, the core electrons can repel easier than having, oh wait, yeah, can repel easier.
Okay.
Did I get that?
I would not.
I think I might have switched Mg2 and 3.
Mg is the right answer, but the explanation is wrong. It's because Mg plus 2 has emptied its outer electron shell. Does that jive at all? Okay. So anytime we have a cation ion, so a positive ion, the cation ion is smaller because when it lost the electrons, it emptied out its outer shell, which occupied space. Now we do not occupy that space. What do you need? Well, you can use this one right here. You just want to be on film. Yeah, I do. Board for the camera. The webcam in your parents' basement as you're playing your Xbox Connect. Is that what requires a webcam?
I don't use that.
Okay.
Although we have it.
Oh, obviously.
I don't want to stand up.
My fault. All right. Number 3. Yeah, these total goals. Which is bigger, O or O minus 2? O minus 2 is bigger. Why? All right. Electron repulsion. Yes. That's great. What'd you say, Brennan? All right. If you say it completed its outer shell, I'll give you 4 out of 5 points. But throw in that last little part that those extra electrons push the electrons farther away. Then you're set. Okay, then which is bigger, Ca or Sr? Sr? How come? All right, it has more shells, it has more orbitals, it has d orbital. Like, there's a lot of ways that you could answer that one. But remember, the lower you go, the more shells you add. A shell occupies volume, so thus it makes it large. Which one of these is bigger? Li. And how come? All right, good. Lower Zeth. That really, like, 2 words. You can get that one done. All right, are you okay with all these? Okay. If you're good, then you're close to, I mean, you're there for what we've learned so far. All right, so let's move on. I never remember exactly where we get in each class. Probably about right here. Let me turn the light off. All right. So this one's not I don't know. I've never seen it tested, but for your information, in an isoelectronic series, ions have the same number of electrons. Ion size decreases with an increasing nuclear charge. So all this is trying to illustrate to you, so O minus 2 and F minus up here, they both have 10 electrons now. Iso means same, electronic, so same electrons, all right? It just follows the same idea that we had before with Zeth, all right? The smaller one, F, will have the smaller ion than the larger one before. That was a big fly for December. I guess it's November. What is that? That's a giant bug. All right, well, I'm not afraid of bugs, but whatever. Are you all right with that? It just follows the same trend. So if I give you two that have the same, the smaller one will be the one with the higher Zeth. All right, where's that dead?
It's moving right there.
Should I kill it?
Yeah.
That would make you all feel much better.
Yeah, before it goes into the lab, it becomes radioactive.
Anybody want it? Good point. All right, good enough. Now, all these things are in your book. If you need more, you can read them. But I'm sure you already did, right? Because you started reading it and you couldn't wait for the next page. Right? You're like, oh. All right, that wasn't funny. That was hurtful. If you're watching a video, they just said they couldn't wait for it to be over. That's like every 1800 Victorian drama my wife makes me watch. I can't wait till it's over. All right, here we go. Ionization energy. So this is a change of topic. It's the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. And that's like a lot of words, but it's just the energy required to take the electron away. All right? The first ionization energy is that energy required to remove the first electron. It's kind of random. Second ionization energy is that energy required to remove second electron. Any guesses what the third ionization energy would be? It takes away the third electron. Now, you got to know that it requires energy to remove an electron from any atom, even a metal. And metals are losers. They want to lose, right? But it does take energy to remove their electrons. It just doesn't take very much energy. All right. This is a really important concept for your exam and for the rest of the year, for you to kind of have an idea of what we're talking about when we talk about ionization energy. All right. So, here's a question and an answer. There we go. The question, really, I should probably go to this graph first. Where is it? Where is it? There we go. It requires more energy to remove each successive electron. So let me scroll down here. Let's ignore Na for a minute, but Mg took 738 for its first ionization energy, and this column, it would be Mg plus 1, right? Mg is not super pumped to be there. It would like to lose its second one, so it takes 1,451 to remove the second one. All right? But then you have a giant leap, and why is this such a big jump every single time? All right. So once sodium loses one, the next one you would remove would be a core electron, right? we don't, in science, we don't remove core electrons. That takes too much work. It's like standing up to play a video game. Who would want to ever do that? All right? So, on the exam, I'm going to give you a question where it gives you like 4 ionization numbers. So ionization level, or 1, 2, 3, and 4, if I remember. And it asks you to tell me what family the unknown element is most likely from. So if, let's say I gave you these values, so we're talking about Mg, let's stick there. And then, I don't know what this would be, let's say it's 9,000 something. If I gave you those, but you didn't know this, you would know that the giant leap came on ionization 3. So it must have been something that was okay losing 2. And family 2 is okay losing 2. You okay with that? It's actually a really commonly missed question, but I don't think it should be. All right. So you will notice that Na has a very low ionization energy compared to chlorine. It's a third as much. Okay? Metals have low ionization energies. Non-metals typically have high. And noble gases, we finally now know why they're really noble. It's because they have the highest ionization energies. So if there's things around them, those things will lose or gain electrons way easier than the noble gas will. So the noble gas just doesn't do anything. You okay with that idea? All right. So then the question was, back here, why do metals have a low ionization energy then? No, definitely not that. They don't share, they lose. Oh yeah, it'd be very reactive. It would want that electron back very quickly. All right. Metals have a low ionization energy because everything we talked about yesterday. There you go. Low Zeph. What is Zeph? I made you explain it at the start. It's the attractive force between the proton and the electron, right? If the attractive force is not very strong, is it very hard to break? No. And so if it's not hard to break, then we would say to ionize it doesn't require a lot of energy. But now you get to the nonmetals, and they are opposite. They have high ionization energies because they have a high effective nuclear charge. So yesterday I made you write a sentence that had the relationship between atomic size and effective nuclear charge, right? So Zeph and ionization energy are related. That's a weird looking D, whatever. Am I going to put the word indirectly or directly into this spot? They're directly. Relationship means as one gets big, the other gets big, right? So as the effective nuclear charge increases, so does the ionization energy of that atom. Because things are holding tight, it requires more energy to remove them. Good enough? All right. There will be a question like this. where it gives you 3 and asks why there's a giant jump for the third. Now, these numbers are not even close, but it was just saying, all right, maybe it took 30 for the second, but now it takes 500 more for the third. Make sure that you understand the giant leap between ionization energies is because you are removing an electron from a inner core electron shell now. There is also a question, that will ask why the second ionization energy for aluminum is higher than the first. We haven't talked about that yet, but any ideas? Go ahead. Okay, that is true. That's not the exact explanation that we'll want. But that's definitely true. What do you think, Newman? That is absolutely true, except for one tiny little word. The effective nuclear charge will stay the same, but the overall charge of the entire atom is now positive. All right? So now you have a cation that's positive, and you're trying to remove a negative from it, but it was more positive than it was before. Okay? So the easy, concise way to say it is because you're removing an electron from an increasingly positive atom. You okay with that idea? I would write that somewhere. That's the answer, Jeopardy style, to the question of why the second ionization energy is always higher than the first. Because you're removing an electron from an increasingly positively charged atom.
So if you're adding electrons, is it easier to add on as you go?
No. As you add an electron, it gets harder because now you're trying to add a negative to an increasingly negative thing. Yeah. There definitely is an interaction between electron-electron repulsion here. It's not as measurable in other instances, but there definitely is an interreaction. Okay, our interaction is what I meant to say. We kind of all right? I know that this chapter's full of just one-line answers, but you got to know them all. Is that it? Oh, Stretcher, looking at your watch again. All right, so here we go. Trends in first ionization energies. This is in your book. You need to be able to explain a lot of these ideas. As one goes down a column, less energy is required to remove the first electron. Okay, so it's saying that it will get lower ionization energy the lower you go. And that's pretty easy to explain. And these are things, if you're a note taker, you should put. For atoms in the same group, we know Zeph is the same, but the valence electrons are farther from the nucleus. So as we go down, we keep making our sphere bigger, right? And it's easier to remove an electron that's pretty far away from the nucleus than it is one that's very close. All right, good. Not yet. Test. Whenever I mute it, I never can remember if I unmute it. I'm poor. What's his face? All right. Now, the next trend, it gets a little bit uglier, but it's okay. Generally, as one goes across a row, it gets harder to remove an electron. Generally. But what Garrett said a minute ago about the S's and the P's, that will be coming up, why there's these dips. But generally speaking, the ionization energies are low here and high here. All right. Now, however, make this a little bit bigger, there are two discontinuities in what we would expect to happen here. That's ugly. There, that looks cuter. Doesn't that look cuter, kids? All right. So discontinuities means that it doesn't seem to follow what we just wrote. And I have these circled here. And they're not that hard to explain, and they're not that hard to understand. Most of the time, pretty easy. Remember, we're talking about ionization energy is the energy required to remove an electron. Oh, crap. Cullimore's coming to get copies that I forgot to make him. Yeah. All right. So these, if we, I won't go that way. If we remember what ionization energy is, energy required to remove an electron, these discontinuities or breaks in the pattern make perfect sense, I think. So the first one lies or occurs between groups 2 and 3. Ignore the A for right now. All right. In this, the electron is removed from p orbital rather than the s orbital. The electron is farther from the nucleus, all right, and it also has small amounts of repulsion by s electrons. Okay, so what we're saying is we have s, we have p, doesn't matter the number, but what we're saying is that these two are normal, and then we get up here. And, oh, that's a line. What is that doing there? All right. So this is representing this drop in this region right here. You with me so far? So what it's saying that it requires less energy to remove this than it would to remove one of those. And that's because this is one electron residing in the p orbital. It's lonely. It's not paired with anything. And the atom would just as soon lose the p orbital in the first place. Also, what Garrett was saying, I'm pretty sure, is that the s being complete is sort of pushing this away anyway, or repelling it. So it's slightly farther from the nucleus. So really, it's a little bit easier to remove that than it would have been to remove one of these that was already paired. Raise your hands if that made sense. Okay, good. That was, I think, everyone that's awake. All right. You must be able to explain these. The problem is you have to be able to explain these in May. And what's today? It's not May. It's almost December, right? So how you remember this in 6 months, I don't know. I would tattoo it to the inside of my eyeballs, but that might not work. Thank you. No, I'm going to move on and assume that you have your own pattern of studying built up in your heart and your mind. And 2 or 3 of you do. The rest of you just don't.
Exactly like, one of those papers that where you write and it goes through the paper into the next one, and the ink goes through. So I put one of those papers on the desk, and then after the smartest person in the class is finished,
That's
I'll
you.
take it. No, that's not me.
Okay.
I'll take it and I'll just turn it in.
Good idea. That's a super good idea. Good luck with that one.
It's impossible.
Yeah, that's weird. All right, you okay with that? The second discontinuity is similar. It occurs between groups 5 and what we call group 6, and it's sort of similar. This time the electron is removed, comes from a doubly occupied orbital. Repulsion from other electrons and orbitals help in its removal. So now what we're saying, we have our S. It's going to be full. We have our P's. So now we have this one, and this one. So now what we're going to be talking about is the removal of this one compared to the removal of one of those. You with me? So what it's going to say is that it's easier to remove this red one than it would have been to remove this blue one. Okay? And the reason it is that way is because what does this blue one do to that red one? It repels it, right? All of the blue ones will push the red ones slightly away. Now, we're not talking giant differences. We're talking like 10. They're not a big deal, but they're a little bit of a drop. And you have to be able to explain both of these discontinuities. Okay? If you look at potassium now, like I don't know if this graph is making sense to you, but it's the ionization energy as we go across the periodic table. Things get really weird, like in the D, okay? Not really weird, but the differences are minute. How about that? So you'll never really have to explain that. Now this drop comes when you have a full D and now you have 1 in the P. It's way easier to get rid of the 1P than the D's. Okay, are you okay with these 2? They're the 2 most important ones. Good? Like you could explain that to me on the test? Because you have to. I'm really feeling like I'm going to test you. And I feel bad even calling it a test. Can we call it a quest? Because it's so short. Yeah, quiz test. Like, I don't know. Which would make you stress more, a test or a quiz?
Yes. A quiz
A
would.
quiz would? Wow, okay, never mind. We have an exam.
Gosh dang it, that's the worst.
Oh, that's the worst. That's the granddaddy of them all, huh? My fault.
The thing is, if you lose 1 point on the quiz, it's worth more than what you lose on the exam. So you have more room for mistakes on the exam.
Okay. So you would like more questions than less.
Yeah.
100 question test over 10 questions.
100 tests. Do you know how long it would take me to grade? You morons writing 100 fake sentences? You're like, I don't know, I'm just going to make crap up. I gotta read that crap you just made up. No.
Yeah.
Multiple choices for sissies.
Yes, thank you very much.
Okay. Whatever. Let's talk electron affinity, which I've already written here, is the least important of the things we've been talking about so far. It's the energy change accompanying the addition of an electron to a gaseous atom. So, hey, this sounds a little bit opposite of what we were just talking about, doesn't it? We were just talking about ionization energy. That's the removal. And now we're talking about affinity, which is the addition. Trends in electron affinity. In general, electron affinity becomes more exothermic as you go from left to right across a row. Electron affinity can be pretty tricky because we're dealing with a negative value, and that just blows minds once in a while. So like these have the highest electron affinity. You with me? Meaning they give off the most energy when an electron is added to them, which means they want the electron more. Okay? Don't let the negative sign. It's only negative because this is an exothermic process, and every time we talk about energy being released, we throw a negative in front of it, right? All right? So things that want electrons have high negative values. I don't know if that's a stupid way to say it. Large negative values. And things that don't, they want to lose, right? They will have very small negative values. Well, I should say, yeah, I already said that. So as you move from left to right, you get a more negative value. Again, however, there are two discontinuities in this trend, and it follows the same idea. It's just a teeny bit backwards. Because we're adding now, not removing. The first occurs between group 1 and 2. The added electron must go into a p orbital, not s orbital. Electron is farther from the nucleus and feels repulsion from the s electrons. So, let me try to explain. By the way, if this part doesn't make sense to you, you'll probably be fine. Make sure, though, that ionization energy and the discontinuities there make sense. So we're talking about adding an electron. So this, we would have a box with one arrow in it, right? So it has room for another arrow, right? You with me? So that can happen. That's not that big a deal. This, we're talking about a box that's already filled. You with me? So it's already got the two filled. And now we're going to add another one. Well, that doesn't want to happen. In nature and chemistry, the P shell doesn't want to exist if it doesn't need to. So it requires energy for these two. It requires energy to do this instead of giving off energy. And these, it barely gives off any energy to add that one. I don't know if this is jiving, but just think about it a little bit reversed. Now we're throwing something on top it doesn't want to be there. Okay, the next one is between groups 4 and 5. Group 5A has no empty orbitals. Extra electron must go into occupied orbital, creating repulsion. All right, so these would be full. These would be full. So what it's saying now is to add another one here takes slightly more energy than it would have to add this one right here. Because these two electrons will repel each other more than the empty shell would or empty orbital would have. Repulsion has a lot to do with a lot of things. But once again, electron affinity is not something that is highly tested or really highly talked about. We talk about ionization energy about 90% of the time, and electron affinity maybe 10% of the time. So don't stress out on affinity. All right. I have no recollection of making this slide. Let's just read through this really quick. Oh, I know what this is. This is essentially my test, what it has been in the past. So these are the questions that I have asked. So why don't you take a couple minutes? You don't have to write down these answers, and I'll reword them because we're doing a whole different test than I've ever done before. But they'll be very, very similar to these. Um, Go ahead. You can take a picture of them. I don't care. That's fine. Check them out and think, all right, hey, I could answer that.